Hi, this is Methamphetamine, and in this video I'm probably going to be very stupid. By that I mean that I'm going to have one statement that I want to prove. I'm going to show you what that is in a second and explain what the words mean. And I'm not going to look up the proof, I may look up some definitions, but the key point is I'm allowed to fail. This is not prepared. You're going to see a raw, unedited version of my attempt, how I organize my thoughts, and how I deal with the whole process. And it may perfectly well be that there's some sort of trick required that I just don't know. Now, why would anyone want to watch this? The reason is, well, it's about failure culture. When I look at my friends, fellow students of mine, then usually you get the vibe that they feel they are worse than they should be because they attempt a proof and they just either totally fail, they don't know where to go, or they overlook something very important or whatnot, or they just forget the most important theorem that they've learned recently or something like that. And I have good news and bad news in this case. The good news is, from my point of view, this is absolutely normal, and from what I've heard from fellow mathematicians or PhD students or whatnot. The bad news is, this is probably never going to go away. It might happen that the problems you struggle with become increasingly advanced, so that would be a plus, but it might very well be that after a few years you will still occasionally struggle with insanely simple things. And yeah, I think that's just part of the deal. So let's go. Oh god, this was a bad idea. No, seriously though. The statement I'm concerned with is... Oh, let me pull up the whiteboard. Yeah, the statement I'm concerned with is about a so-called partition of unity, and I'm going to assume basic topology knowledge here. The theorem is a topological space is paracompact. I'll explain what that is in a second. If and only if, and I'm probably gonna abbreviate that by if with two F's, which is a very frequent stylization. Every open cover, and I'm going to take this open cover to be indexed, which means that I'm organizing it as UI, where I is in some index set, admits a subordinate partition of unity. This is very important in, whenever you're dealing with, well, stuff like manifolds. The statement is covered in a differential geometry course at my university. But, well, to be perfectly honest, I passed that course without ever proving that or looking at the proof, so yeah, there's that. What does paracompact and what does partition of unity mean? I think these are the... well, partition of unity subordinate to a cover. Paracompact means that every open cover has a so-called locally finite refinement. First, let's talk about what a refinement is. A cover VI is a refinement of well, they can be totally different covers, so I'm going to take different index sets. If every vi is contained in some ui. So essentially all the sets in the cover V are necessarily smaller than some set of the UI, so it has to be finer geometrically, which just means you cannot take huge clumps. That was a stupid way of wording that. A cover is locally finite by the way, I'm going to add chapter marks to that so you can skip these boring definitions, but we need to lay out some groundwork. If for every x, I'm going to fix the topological space x because we're not going to consider other ones in this this thing. So essentially it means that around a neighborhood of x there is only finitely many covers touching that. Yeah, finitely many covers. What would it precisely be? Finitely many elements of this cover in which this x is contained in, but not only the x, the neighborhood of x is contained in. So there is a neighborhood, well, or an open neighborhood. This doesn't really make a difference. In fact, these statements should be equivalent. I'm fairly certain of that. Let's call it O. No, not it's not containment. I wanted to write that such that O is contained in only finitely many covers, but then we could just take O to be all of X, and then there's only one element of that cover, if any, in which O is contained completely, which is just X. So, and if X is not in the cover, then that's what we actually mean is. What we actually want to have is that O is disjoint from all but finitely many covers. So that the set of all elements of this cover such that they have non-empty intersection with O is finite. I should definitely look that up, because if I get that wrong, then I will be totally lost in what follows, but I'm fairly certain that this is the case. Yeah. And a locally finite connection. Yeah, if each point has a neighborhood that intersects only finitely many sets in the collection. This is true. Okay. You're gonna notice it's takes a lot of time to pin down many of the definitions, but it's important to be detailed there. Okay, so X is paracompact if every open cover admits a locally finite refinement. This is very abstract and useless, and why paracompact spaces are useful is essentially due to this theorem we're trying to prove. But let's sort of talk about partitions of unity, because I'm very, very doubtful about whether that theorem actually holds, or whether that only holds when we have additional knowledge about our topological space X, such as it being Hausdorff, because this is very often silently omitted. Oh, topological spaces are always Hausdorff, because who would do stuff with other spaces? But yeah. Oh, trust me, you're gonna need the chapter marks. This is going to take a long time. Now, a partition of unity is essentially a collection of functions that between 0 to the real numbers, which is non-zero precisely in a set of the cover, because very frequently we can describe a space locally, and in the case of vector bundles, say we have local trivializations, or in the case of integration over a manifold, which is a space where we just locally know how it looks, well, we're going to locally look at it as Euclidean space and define the integral over that, but well, we have to multiply with something that is 0 outside of our cover to get from some local description, some local entity, to an entity that is actually defined over the global space. If this doesn't make too much sense, then don't worry about it. It's really to just provide some mental bridges. The formal definition is as follows: is a set lambda I such that I'm not sure if we can just write it as first of all, we should define what the lambda i's are. These are functions from X, from all of X, by the way, to the real numbers. No, not all of the real numbers. We want only the portion between 0 and 1, both things included, such that the sum over all I in the index of lambda I is 1. And in particular, notice that an index set I, well, we didn't specify whether I had to be finite, right? We didn't even specify the cardinality. It could be just continuum or whatever, something incredibly huge, but we want this sum to be well defined. We want them to be continuous, by the way. All functions we're concerned with are continuous. For all x in x. So this is well defined if it's point y for every point as a function. a well-defined sum. So, and this sum is only then well-defined when, no, not only then, it might converge, but what we want is that there are only finitely many indexes where lambda I of x is not equal to 0. Because then we're taking the sum over all the values lambda I of x for all I, but well, most of them are just 0, and the only ones contributing to the sum will be the finitely many lambda I for I in this set, and that's a finite sum, so this gives a well-defined number, and this is precisely what we want. Now, lambda I is subordinate to ui I could have just used normal parentheses, but yeah. If, well, essentially the only place where the lambda I has any value is contained in ui. So if the support of lambda I, which is the closure of the set of all x where lambda I of x is 0, is a subset of ui. Okay, now one of the directions should be rather simple, so I'm going to focus on the other one, because the other one is real work. So this should be simple, I have been told. Yeah, I think the idea here is that if ui I is a cover and this guarantees the existence of a lambda I partition of unity which is subordinate to ui, then, well, we're looking for a refinement, but I think we can just take the support of the lambda I as a cover, or well, the interior of the support, like, yeah. Should we call it the pre-support? Let's call it the pre-support. Let's just make up words for it, because you're noticing here we're taking the closure, and this is a closed set, the support, but what we're interested in is an open set, because we want to have an open refinement of this set, and this is the open set we want. It's unequal to 0. That's what I wanted to write. This is an open set because this is just lambda I, the inverse image of this set, which is all the elements of the codomain which aren't 0, and this is an open set in the closed interval 0, 1. I could just have written 0 or infinity when the codomain would have been all of R. So yeah, this is an open set, and we mean that, and let's call that the pre-support. So when folks skip this video 10 minutes ahead, they will have no idea how the pre-support is going to be defined. Isn't that great? Okay. Let's continue. Then I think, I've not proven this, I think the presupport of the lambda I should be a refinement and should be an open cover. So it's open, does it cover it? Well, at every point there must be lambda i's which are not equal to 0. So at every point there must be some index where the presupport contains this x, and so this is definitely an open cover. And yeah, for every I the presupport is contained in your I. So yeah, we're actually done with that. That went well. But this was the easy direction, and now I know why it's the easy direction. So now for the difficult part. New page. Can I select that? No. Don't care. Let x be paracompact and fix an open covered UI. We want a partition of unity subordinate to UI. Now, what's confusing me about this is that, well, first, in my mind, I have no idea how to prove this, but let's just take a very, very simple case. Let's take 0, 1 with the open cover I don't know, 3/4 and this is not a 4, this is a 4. Okay, and 1/4, like just it doesn't even matter, just an open cover like this. And so we would have to prove, using only the paracompactness and no other property whatsoever, that there is a, like something like this. If this is 1 and this is 0, no, it has to be, like, it has to be precise. Let's just paint this in real quick. So here this function has to be 1, and here the other function has to be 1. No? This is u1, this is u2, and this is supposed to be lambda 1, and this is supposed to be lambda 2, and lambda 1 should be somewhere, this should go something like this, right? But how do we prove that something like that exists? In the real case, we could just, I don't know, come up with some function that has these properties and take, so lambda 1 is some function that is 1 and something here where we just don't know it. And lambda 2 could then just be chosen as 1 minus lambda 1. Right? And it had to be, yeah, okay, it had to be. There isn't any other possibility. Because if lambda 1 wasn't precisely 1, if lambda 1 was something like this, here, because notice that we don't want that lambda 1 is precisely 1 in the complement of all other sets, but it has to be because there couldn't be possibly any other part of the partition of unity contributing to the total sum of 1 at this point. Like lambda 2 has to be 0 here. So everything of every part of the 1 has to come from lambda 1. So this is completely impossible. So that's a valid starting point. But, I mean, we could just know that there is such a function on the real line between 0 and 1. But with this theorem, we should be able to prove this for any topological space that's paracompact and any two-element cover, right? And this is supposedly the most easy, non-trivial case of a cover. Like with a single cover, you can just take the one function. That's easy. But if we take a cover of two elements, then it should also work for a paracompact space. And usually, to prove the existence of such a function, you need something called Urysohn, the Urysohn lemma. Which guarantees that two closed sets in a, I think, normal space. You need some separation property at least. It's I have not remembered the details of that, but you need some additional requirements on this space, so this holds, and it enables you to, for every two closed sets, I think, find a function that is 1 precisely where the one closed set is, and 0 precisely where the other closed set is, I think. No, not necessarily precisely, but something like that. It doesn't really matter because we cannot use it. We don't know if this space is normal or something like that. So yeah, I think we will have to try to use the paracompactness to build this function. Okay, so I'm going to look up the definition of the statement of the theorem, if there's any other properties we can use. But I'm fairly certain that we cannot use anything else. So oh, yeah, okay, we do have... Okay, yeah, never mind. We have Hausdorffness. Okay. And Hausdorff is... the Hausdorff property is frequently called T2. Oh boy, this is going to take a long time. I'm afraid I'm missing a lot of context about Urysohn, the Urysohn lemma, and do we know that? Perhaps. Let's just try to see whether paracompact Hausdorff spaces are normal. Normal, to recall, Hausdorff was given 2 points, you always find disjoint opened sets around 1 and the other point. In other words, disjoint open sets that separate these two points, and normal is the same thing with closed sets. You will always find disjoint open sets separating these closed sets. Or was that regular? I think regular was weaker. Again, no shame in looking up definitions. A normal space, yep. mean, perhaps that's wrong, so I kind of risk at trying to prove something for half an hour. Oh boy, this is going to be terrible. Trying to prove something that can possibly work. But hey, that's kind of the reason for this video. Another thing I kind of recall is that if we do have a Hausdorff space, so let's take n for a node. Yes, this is white, but this is an ugly n. That T2 implies that closed subsets of a compact set are again compact. No, this is complete bullshit. This holds true everywhere, but what I meant was this is not too hard to prove actually, because for every cover of the closed subset, you can just take the complement of that closed set, which has to be open, and add this to the cover, giving you a cover of the whole space, and then you use compactness, giving you a cover of, well, this compact set, and then you use compactness of that compact set, and then you throw this one set away. And this holds everywhere, but in Hausdorff spaces we have that compact spaces are always closed. And by the way, this is sometimes called the KC property, or this turns Hausdorff spaces into KC spaces. Because K is very frequently used as the symbol for a compact set, because of the German word Kompaktum, I guess. Perhaps not. That's how I remember it. So let's A and B be disjoint and closed. Is there any canonical way we can get a cover? Well, we could take the complements of these set, but then the paracompactness would give us, well, there is a locally finite refinement of this cover consisting of two sets, which is this cover, because it only has two sets, so it has to be, it's finite and hence locally finite. So this is kind of useless. Again, perhaps I'm just completely wrong. Is there any other thing that we... Oh, bullshit. No, we wanted to show that these sets exist. No, we wanted to show that open sets surrounding these closed sets exist. Okay. Bah. So I'm thinking about whether the compact subsets as subspaces, do they have to be paracompact as well? I would think so. Because again, you would probably be able to extend it to a cover on the whole space. Yeah, should be true, but let's stay focused. Let's just put that, remember it as an intuition to guide us towards something that could work. So So for any pair A and B, we have UA and VB. Ooh, let's do something simpler. We should probably... I'm thinking that given different points, we can get different open sets. And if we... covering this point and separating stuff from the Hausdorff property, and if we take lots of different... like all the points in one closed set, then we should definitely get a cover of this closed set. And perhaps this will lead us somewhere. But let me take a quick toilet break. Okay, yeah, let's continue. I wanted to show something simpler instead, and namely the regularity property, where 1/2 of this is a point, and 1/2 of this is a closed set. A in X and B in X closed. So we have this situation. So it's definitely true that being a Hausdorff space does not imply being a regular space. So this is normal and this is regular. How do I know this? Well, it's just been too many times that I've opened the Wikipedia article about all the separation axioms, because it's a fascinating topic. Like, you think there's just so many ways that you can either separate things or not, because you usually work in metric spaces at the beginning, and then somebody tells you, well, but let's just weaken the assumptions and allow for terrible, terrible spaces, and it turns out there's a huge variety of things that can hold sometimes and not hold one time, and just separation axioms are one of these things. And yeah, so for every element in B, choose a UB around A and a VB around B. Open and disjoint. Existence is guaranteed by the Hausdorff condition, right? Then so like we do have this huge amount of sets for every A, for every B around A, and here around every B we have some set, but the B's lie somewhere different. And so this would be a cover of that set. But the problem is, it might be that the set we're getting for one point is inside of that union. Can we fix that somehow? I mean, perhaps it's just not true. Perhaps there are paracompact spaces which are Hausdorff but not normal. So then this is a B, this together with this covers a together with the closed set B. Does this get us anywhere? I'm not seeing anything obvious. Perhaps this is a mental image that's too complicated. Perhaps we should really try to reconstruct such a function from only the paracompaktness of this real line. By the way, I have assumed that the real numbers are paracompact, and I'm really certain that it has to be, because else a ton of different stuff wouldn't work. For instance, this is a manifold, and I have learned that manifolds always are paracompact if they're second countable, but this is... So there's a multitude of areas and higher level arguments. So I'm pretty confident at this. I think if you... Like, compact spaces are definitely paracompact, right? Because for every cover you can just take the finite subcover that's guaranteed to exist, and this is by definition clearly a refinement of this cover, because every element in the subcover is contained in an element of the original cover, namely this element. And I recall that when a space is made up of a countable union of compact sets, in an increasing countable union of compact sets, then it should be paracompact. Yeah. So my intuition for this paracompactness, where I formally try to put it, is compact spaces are really small spaces, like points of finite sets, or something like the disk, the closed disk, or the closed unit ball of some finite dimensional vector space, or Euclidean space, or something like that. Like the open interval isn't compact because this is homeomorphic to the whole line R, so it's not small in the same sense as compact sets. But paracompact is something that's similar but weaker, and it's also something I would consider a property of small spaces, because I recall that we needed the second countability condition in the definition of a manifold to achieve this countability. So I would assume that there are spaces which aren't paracompact, who are not second countable, because they are not second countable. And yeah, but this is most of this. Lots of that could be wrong. This is just how I build my intuition right now. And so paracompactness is something weaker than compactness, but still similarly behaved. Let's go to the real line. Again, let x be 0 and 1, and u1. Ah heck, let's make our lives a bit easier. 0 and 3, which is topologically the same. u1 is, why am I doing that? 0, 2, but not including 2. And u2 is defined to be 1, 2, 3, not including 1. Okay, the question is, how can we build a function like the one we had at the beginning, an f or a lambda 1? Now let's make this right. And by right I mean horribly ugly. 0, 1, 2, 3. Ba, 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 ba. Ba, 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 ba. There's 1, there's 1, there's 0. And here we are 1. And the set of points where lambda 1 is 1 has to be a closed set, because it's the pre-image of the set containing only 1, which is closed in the real numbers. And the set where it's 0 has also to be closed. So this is in there. And we want something. Let's just take something monotonically decreasing. It doesn't have to be. I could have a bump in here, and it doesn't really matter as long as it becomes 0, because recall that lambda 2 had to be just 1 minus lambda 1, and then it works, whatever it is in this intermediate area. So how can we build that? So we have these two values given, no? We have 1 and we have 0 here. Can we just, well, what do we know about that? Okay, so we know that if we pick these 2 points by the Hausdorff condition, they can be separated by open sets. And let's let this point be on the boundary. So whenever we have a different example, this still results in our open set containing elements which are not in our set u1 without the closure of u2. Yeah, precisely. It's on the, yeah. So what are these sets? This is u1 without the closure of u2, which is an open set. And this is u2 without the closure of u1. And this here is, this goes from here to here, and in the middle is u1 intersection u2. Oops. I'm just thinking about something. Imagine take x equals to 0, 1, and take the following cover consisting of, well, 1 plus 1/2, 1 plus 3/4, 1 plus 7/8, no, yeah, 1/2, 3/4, quarters, 7/8, and so on and so forth. So this is U, let's call it U2 or U1, U2, and so forth. So this covers all of this interval, and paracompactness gives us not a subcover that's finite, because this isn't possible. Any finite subcollection of these sets can only cover a portion going to, well, there's a maximum element of that, and it cannot possibly cover everything. So the paracompactness needs to ensure a refinement which is locally finite. Okay, so why isn't this locally finite? It's locally finite. Okay. It's not locally finite because this portion here gets visited infinitely many times. So there's infinitely many sets intersecting there. So what this might do, the paracompactness, is that we might just make U2 as small as it could possibly get while remaining open, and still covering the new elements which it doesn't cover, which it's seeing for the first time. Like every set of the cover has to have a reason for being there. Well, of course, there's nothing speaks against adding this set to the cover, but for a locally finite refinement, we could just ignore it because it doesn't add anything to the cover. It doesn't cover any new ground, so to say. So yeah, what we could do is this is 1/2, 3/4, and this is I don't know, this is I don't know, and so on and so forth. Oh god, this is going to be ugly. But hey, well, we don't have to show that this is paracompact. We have to use the paracompactness to construct things. Okay, but this is we should keep that in mind. Okay. By the way, I'm drawing this two-dimensionally here, although it's meant as a one-dimensional thing. So let's just erase that. Oh god, this is going to be terribly wrong, but I promised a raw and uncut version. Also, posture. Care about your posture, don't be like me. Does this give us a covering? A cover of our space? How can we use paracompactness? I think once I get that, I definitely should be a step closer. Ooh. Couldn't I take something ridiculously large that approximates the closure or something? But then I'm not quite sure how we would use the Hausdorff property, to be honest. I'm thinking about whether this approximation idea of a closed set would help us with the regularity thing. And we could just let's just use let's try the normality, because then we would get we could let A be disjoint closed, then and take crap, no. Well, let's take U non-empty. Let's take a non-empty open. So, is this guaranteed to exist? Like, my idea would be that consider the set of all U such that U is disjoint from A and like open, of course. Every U is open, you know that. Disjoint from A and U is larger than B. Non-empty, it contains the complement of A, which is in fact the largest set satisfying these properties. Does that lead us anywhere? Now we know that there exists, provided that the complement of A is still paracompact as a subset of a paracompact space, or a subspace of a paracompact space. Let's just hope that. So you know how there exists a unique, and there exists, but I don't really know what I'm talking about, so probably, perhaps, a locally finite refinement VI of this U. I haven't bothered to index it because the indices don't matter for the definition of a refinement. Of U. i.e. every VI is I forgot how to write. In some U disjoint, so in some, for every I there is a U, and we can call this U UI because U depends on I, disjoint from A and UI does that. Does it help us anything? Because it might as well just be here, right? Well, we do know it's locally finite. What the hell does this local finiteness bring us? Oh god. Okay, what else do I remember with finite? Having something finite is good if we want to intersect open sets. Ooh. Okay. Oh yeah, observation. Um, for every x, there have to be only, and there is some neighborhood such that um, such that uh, the set of I and I is we have finitely many elements of that cover satisfying some property. My idea is, let's just intersect it and see what happens. Because, well, that's a new special set we're guaranteed to have, which hopefully just retains some things of our locally finite refinement. Um, so for any locally finite cover, we should have around every point x one distinguished set, which is as small as it gets, because it's the oh crap, the intersection can be empty. Ugh. Oh god, this is ugly. Let me just draw the visuals I have in my head. So around every point there is that, such that there are only finitely many things in our cover intersecting that. My thought was, hey, let's just intersect these things, these bad boys, and let's get a small set, but this small open set could, just be empty. Also, I don't really know where I'm going with this. Okay, how do we build a function? We can define a function by saying, okay, on this closed set, you're gonna take that value. Because essentially I can define this function by saying, hey, at this closed set, for instance this, you're gonna be 1/2. At this closed set, which happens to be just a point, you're gonna be 7/8 or whatever. If I do this for... I need a partition of my space into closed sets, which is nice in the way that okay. I need to organize disjoint closed sets in a way that I can linearly order them. So I want the function defined by that to be continuous, and continuous as a function into the real numbers. And this essentially means that I have to find a linear order on them. I think this is a key insight. Okay. So remember, this is U1 without U2, which in our case happens to be closed, but doesn't have to be, I think. This is U2 without U1, and this is the intersection, U1 cap U2. How do we know, not by looking at this as a subset of the real numbers, which is why I didn't bother putting any numbers on that, because it has to work in every context. How do we know from T2 plus paracompactness that there is a partition of U2, U1. And U2 into enclosed subsets which admits a linear order. Okay, this with the linear order is probably not enough, because if I have something two-dimensional like that and this, I could say, well, this is 1, 2, 3, 4, and this will be a linear order, but this wouldn't turn any of that into a continuous function by saying, well, you're 2 everywhere right here, but not on 1. What is that? Okay, no, that isn't clearly isn't disjoint, but my point still stands. If I say, well, this is going to be 1, and I have this point here, and this is going to be 2, and this is going to be 3, if the topological space is somewhat isolated, that this would actually be a partition of closed sets, and I pick this to be 3. And what if I would pick this to be 3 and this to be 2? This would also be a linear order, but because these sets are disjoint, no linear order is really better than the other things. So the sets being disjoint probably won't help us really. Yeah, sucks. Perhaps we have to use... Okay, let's just assume X is connected. Just for the baby, because why not? Should make things simpler. Hey, I'm back. Sorry for the short interruption. I took a break. But I found some time to think and let my mind wander. I got nowhere really. I'm still mainly confused about how the Hausdorff property and the locally the paracompactness is enough to prove the existence of a separation function, because the Urysohn lemma provides precisely that, yet it definitely needs to require, well, perhaps not normality, but something weaker, but it was definitely not Hausdorff. So just a space being Hausdorff isn't enough. But I have absolutely no idea how we're going to get some cover in the process of trying to construct that, and then getting a locally finite refinement, and how this is going to help us with anything. Like, this is just insanely confusing to me. Yeah. Perhaps we should assume furthermore that X is compact. And let's just strike that. accurate. Can we, for instance, say that the function has to be 1/2 over here? Oh, but then, Or how do we know? I think that's a better question. How do we know such a point in the middle exists? Okay, well, U1 cap U2 is non-empty. So pick x1 in there. No, we should, I think we should do this differently. We should not pick the set where the function is going to be 1/2. We should pick the set where the function is going to be less or equal than 1/2. Less than or equal to. Why is there a closed set bigger than U1 without U2? That is significantly larger than U1 without U2. Closure of that. Because this is the set where we only take the value 1. We want to take the value 0 somewhere else. In other words, yeah, let's strike this significantly larger. We want it to be larger than this period. So because we don't have normality, we can't just say, oh, we have the left strip, U1 without U2, we have the right strip, U2 without U1, and we can just separate them by open sets. In this case, we're lucky, because there is only one point at the boundary, and we can just use open sets to these are, oh wait, these are compact, right? Can we work with compactness? Yeah, we assumed that X was compact, so we know that this closure is compact. So let's just use that assumption. Okay. Wait, is any compact Hausdorff space normal? Is any compact Hausdorff space regular? Because I'm thinking like when we have one point and not too sure about that. Yeah, you realize my thoughts are not really well organized because I don't know a lot of detailed statements about these topological facts. So yeah, so why is there? Let's just take R2 as a different example, which makes things a bit more difficult. Let's assume I have these sets, yeah? Right? And how do I know? No. These sets, yeah, these sets are the closure of an open set. And how do I know that there exists that? So this is U1, this is U2. I'm not sure if this is possible without recovering that the space has to be normal, which seemed like a much stricter statement. Okay, I think we would like to. This closed. What I'm thinking about here is that the larger closed set could also just add this, but we want that the closed set is the closure of some open set that's containing the closed set, because I think this would get us where we want, namely that that the new set we have is a neighborhood around every point of the original closed set. That's, I think we should write that down. So should be a neighborhood around any x in U1. Sorry, German leaking through. For every x in U1. In other words, every point in U1 is interior to this larger set, so U1 is in the interior of this new set. So the question is, can we find an open set which would be this interior U1 prime containing U1? Let's just say the no, it's not U1. Why did I call this U1? Our U1 previously was the element of the cover which had non-empty intersection, but what we care about is U1 without U2, so let's just call this open set A, this closed set A, and this is B, so we have A, and here we have, come on, that looks sloppy, A, and then we have B. So yeah, we want a V1 containing A such that the closure of V1 disjoint from B. Because, well, all the elements in B already have a designated value. Our function should be 0 there. But we want to interpret this closure of V1 as the set of all elements greater or equal to 1/2. So V1 closure should be should correspond to, or we wish that it should be the pre-image of. No, let's just write it informally as the values smaller than or equal to 1/2. So the boundary of V1, which is the boundary of the closure of V1, should correspond to the values that equal 1/2. Like, right? This, if this is the closure of this open set surrounding A, then this should be the boundary. And V1 closure should be everything. Pause check. Okay, I wanted to look up no results, but perhaps I should really look up the Urysohn lemma, whether there's some kind of simplification, some kind of different context where we can use it. If not, I should probably try to prove normality from paracompactness. But this stuff seems like really hard until you know how it's done. I hate that. Can we? Okay. Okay. Let's do it as follows. Can't we pick any point in the intersection and not say, well, it should be 1/2 there, but let's say it should be greater than 1/2 there, because there's space. It should be somewhere later, and then we could use this point to separate this point from every other point with the Hausdorff property of A. This should give us an open set that in every case is still disjoint from the point. Yeah, this should... Okay, but we don't necessarily know... can we... So, if we're unlucky, this open subset around the other point in A could be so large that it touches B. But we could always... Yeah, we could always take it to be... Crap. Not in B, but taking the intersection with B's complement. So set minus B. But then, like, let me illustrate that. My idea would be that we have A, we have any point, and we have B here. So this should have value greater than, so we have 0, we have 1. This should be greater than or equal to 1/2. And by this, and by virtue of being able to separate this point and any other point here by open sets. We could be so goddamn unlucky that the open set looks something like this. And we could say, okay, then take set minus b, but then we would be left with an open set that whose closure touches b, by which I mean whose closure has non-trivial intersection with b. So, but we want to use this set and all other sets separating points here, let me color that differently, to get such an open set containing a. But we want this open set containing a to only represent values that are smaller than or equal to 1/2. But if it can like touch b, then yeah, we want the closure to represent all values to correspond to 1/2, but so it cannot touch b. So it cannot have any non-empty intersection with b because b is already reserved for all values that go to 0, that not go to 0, that have the value 0, that get mapped to 0. So this is incredibly bad, right? So we could use another open set here that gets separated by another open set there. So yeah. I mean, compactness shouldn't give us any separation property whatsoever because, well, for instance, there are finite non-Hausdorff spaces, which is, yeah. And being compact and Hausdorff, I'm not sure whether that implies anything. Okay, but let me just analyze there exists a locally finite refinement of a cover statement, and see what kind of constructions it allows for. Because I think if Vi is a locally finite refinement of Uj. Come on. Then for every x there should only be finitely many elements of the cover containing that x. The set of Vi, or the set of I in I such that posture Vi contains x is finite. The reason for that is that this here happens whenever Vi intersecting x is not equal to 0, and so this whole set is a subset of the of all the indices where vi cap some neighborhood isn't is non-empty. So this is a subset of this for any neighborhood around X. And in particular for the neighborhood around X, which is guaranteed to have only finitely many. So one of these collections for every n must be finite, hence this here must be finite. Call this Ix. Let's introduce the notation Ix. And Is for any set could be defined to be the set of all indices where the sets have non-empty intersection. This might help organize our thoughts. So let vi, I in I, be any locally finite system. Then, so the definition sign should go before that. Is is defined to be the set of, this is ugly, I in I, such that vi cap s is non-empty. By the way, this is doing nothing new, but just giving the idea I had before a symbol. This is a construct that is possible because of the local finiteness, and often it helps me a lot just to introduce some notation to organize the thoughts better, because some statements can be made shorter with that. And let's abbreviate as the shorthand Ix. This is for all S subset of X. This is an abbreviation for I with this X. I with the set of X. For X in X. Okay. So now the observation I made, reformulated, is first, if S is a subset of T, then there's more possibilities for sets to intersect with S if S grows to T. So this should be the case, right? Because if I is an index such that it has non-empty intersection with S, it certainly has non-empty set intersection with the larger set T. Okay, that's a good thing. 2, local finiteness implies for all X there exists an open U containing X such that U is finite 3, this here implies that for all x in x, we know that x is in x, this is just visual noise. For all x in x, we have in particular ix is finite. Okay, so note the intersection of all vi for I in this collection ix is open and contains x. Hence is non-empty. It's open because we take the intersection over finitely many open sets. Okay. So for any cover, there is a locally finite refinement, so there is some, around every point, some open set that has to lie in that refinement, that has to lie in that... Oh, wait. I mean, this... Just getting some open set around a point x isn't really gonna help us, is it? Are there different properties of this vi? This is excruciating, but you know, this is the real deal. So yeah. It's normal to get frustrated at some point. But yeah, I've made a commitment, so I'm going to just exemplary try to push through, and I'm probably not going to get this today. So yeah. Let's just try anyway. I'm gonna give my best. This is what it's all about. So this is an observation. We don't really have a plan at the moment, right? We just try to use that knowledge. Wait, we have one property here. Ah, crap. No, this isn't helpful. I wanted to say, if we have any cover, then there is guaranteed to exist a locally finite refinement. Hence, by virtue of these sets, around every point we have an open set which is inside some element of that cover. But we always have that. Every open set must be covered. Every point must be covered by some element of the cover. That's why it's named that way. So but vi no, we already have that it wait is this no. Can we make it smaller? Oh, wait. So we have all the sets, precisely all the sets of this refinement, which contain X. So if we intersect it with any other VI, we do not contain X anymore. And intersecting with an open set is the same as intersecting the complement of the complement, which is the same as taking set minus of the complement of that open set. Doesn't help us. Doesn't help us really. Yeah, I might seem a bit calm, but in reality I really want to punch a wall here. Or the screen, but I don't like broken screens, so there's that. Okay, fuck it. Let's just look up the Urysohn lemma. Yes. No, of course it's Urysohn's lemma. Yeah. Oh, yeah, it's a characterization of normal spaces. So do we know anything? Ew. Oh, all compact Hausdorff spaces are normal. Why did I not know this? Okay, let's show this. Because this, okay. Okay, this is a game changer. Because then we could, I think we could better be able to try we know some functions separating these sets exist, and we then just organize these sets in a good way that we can adjust it, take 2 sets into account, take 3 sets, and so on and so forth, and make our function more and more focused, so to say. Yeah. Compact Hausdorff implies normal. WTF. I kind of expected me to know that, because I've so often heard people talk about compact Hausdorff spaces, and it never occurred to me. So X compact Hausdorff, X normal, let A be disjoint and closed. My idea would be first to brute force it, and for every element here, take open sets, doing this skedazzle. For any A in A and B in B, choose separating open sets. We're going to call them U UAB and VAB. So U is always around A, V is always around B, but both U and V depend on the choice of A and B. So, hence the subscript. Okay. Now, UAB for all A and all B, the collection of those covers A, and VAB for all A and B covers B. Closed in a compact implies that this is closed. Wow, that was a terrible way to draw an arrow. And by closed I mean this. So there exists a finite subcover UA1 B1 to UAN BN and the same for V A prime 1 B prime 1 until V A prime M A prime B prime M. This is a cover of A, this is a cover of B. How does that help us? Okay, we can take the intersection of those bad boys. But how do we know that the open sets we get are in fact disjoint? Okay, first let's make a small adjustment. We are not taking, so without loss of generality, UAB intersecting B is empty, and VAB intersecting A is empty. Why without loss of generality? Well, because we could just take a different cover by taking UAB without B, and this is still open and still a cover of A because A is disjoint to B, and still open because B is a closed set, and we can scrap away closed sets from an open set and remain open because it's just the intersection with the complement, and complement is open. So yeah, without loss of general, and here we could just take without A and get a cover which has empty intersection with A. Okay, so that guarantees that we have but we have at least open sets. So this might, my idea would be take the intersection of all I of UAIBI. This would still be open, Because all the AI and BI, well, there are only finitely many of them. So we have finitely many open sets, and then we can intersect and still get an open set, which is like smaller than most of the rest. Yeah, but and here intersection of bj of uaj prime bj prime. I'm ignoring the limit bounds here because who cares about that? So we might have something like this. Perhaps we should take a step back and show that X is regular, because we're trying to do things at the same time, like cover A and cover B. So perhaps let's just fix an element B. Okay, sorry, I had to care about messages and mute people. Yeah, so let's A in X and B closed, A not in B. Then separate separate for all B, separate A and B by U, B and VB, without loss of generality. UB is disjoint to B. Let's take UB dot B. So, sorry for being a bit unreadable. So, that UB1 VB1 VBN a subcover, a finite subcover of B, and consider V defined to be the intersection of I of VBI, and U defined to be the intersection of I of UBI. This, of course, still covers the one element set X. By the way, points are closed in Hausdorff spaces, in particular because you can take one point, and for every point not equal to that point, separate that point with an open set, and then you just take the union of all these open sets, and the union of these open sets must be all of the complement. So the complement of the point is open, hence the point is closed. No, points are not always closed in topological spaces. Weird shit. So we have V around the point. No, we have V around B, and we have U around X. Now, okay, yeah. Is, oh no. This, yeah, this covers X, but we don't want that. We want union of that. Because we want a cover of B at the end. We want an open set containing B. If we take the intersection of this finite subcover, that would be stupid. That would perhaps only cover a tiny part of B, but not all of B. So yeah, I mean we have hopefully our union of stuff around B. Oh, we called X A. And okay, is U intersecting the empty set? Okay. We know for all oh god, yeah, this is the point where I'm going to be really nervous and not get that, although it's probably incredibly easy. Let's just hydrate, that always helps. This is nothing but saying use in the complement of V. So, yeah, U is in the complement of V, which is the same as saying the section of I of UBI. No, this is precisely the same, because, yeah, simple to prove. This is the same as saying UBI is in, well, is the complement of V. Well, it's by De Morgan the intersection of the complements. Oh yeah, precisely. But for all I, UBI is in the complement of VBI, because UBI cap VBI is the empty set. Hence, yeah, taking the intersection is a monotonous thing. Let me think about a unnecessarily elegant way of showing that. A is a subset of B if and only if the intersection of B with A is A. So we could show that the intersection of hence oh wait, can we just no, the intersection of all I and j. So yeah, the intersection of all I, let's go really formal, guys. This is completely unnecessary, but let's go really formal. Of ubi intersected with intersection of all, let's use a different dummy index j for vbj complement, is the intersection of all I, the intersection of all j, because nothing here depends on j. ubi vbj complement, intersection of that complement, is the same as the intersection of all I, no, is contained in the section. Oh, this is completely bad because I just wrote under my thingy. Let's just move. Infinite whiteboard for the win. Yeah. ui subset of vbi complement, we know that the intersection of these is part of the intersection for all I and j. So this is the intersection of all I and j with I equal to j, which is a subset of so this here lives in 1 till n times 1 till n, and this here lives in the diagonal subset of the cross product. And wait, this is the wrong way around, isn't it? Yeah, but this is contained in, so yeah. So the diagonal is a subset of this index set, but the intersection over a smaller index set, so the intersection over fewer sets, is always potentially larger. Oh yeah, that was right. It's potentially larger. So ubi cap vbj complement. We know that because ubi is a subset of vbj, this is just ubi. Yeah, precisely. This is the same. So this is the same as intersection of all I of ubi. This is because ubi is a subset of vbj complement, of vbi complement, because I equals j. So yeah. Well, it's not really elegant, it's just unnecessarily complement. So yeah, what we have shown is that if this intersection is a subset of this intersection, that was complete bullshit because this is tautological. Wait. No. If we intersect, yeah, if I intersect two sets out of the three sets, this is going to be, yeah, okay, wait. Is this even true? Let's just ignore that this happened. And okay, let's just prove it directly. Like, Assume U were in U. Then for all I, U were in UBI, hence U not in VBI. If U were in V, then U had to be in VBI for all I. Okay. Yeah, okay, it's, yeah, incredibly easy. I completely overcomplicated it, because this contains the intersection of all I for VBI. So in particular, you cannot be in the intersection. Jesus. Yeah. Yeah, but we showed that if a, so U contains X, V oh no, I forgot that V was the union. We want to show that the erg. Okay, so okay, yeah. Wait, what was... Ah, no, I pressed insert. Yeah. But still, U not in VBI for all I implies U is not in the union. If U is not in any of them, then it's not in the union of the VBI, which is by definition V. So we know that U contains X, V is a cover of B, and UB is intersected B is empty. U open, V open, and hence we show that these two can be separated. Just to double check, because I tend to do very, very stupid things. Why is U open? U is open because it's the intersection of finitely many open sets. V is open because it's the union of finitely many open sets, and the union of arbitrarily many open sets is open. U contains X because by definition all the UBI we intersected contained X, right? Contained A. Called it A. Did it again. And, well, every element in B must also be in V, because every element in B is because is in some VBI, and because VBI is by definition a subcover of B, a subcover of a cover of B, so it also covers B. Yeah. Okay. Wow. So we know compact Hausdorff implies regular. Theorem compact Hausdorff implies normal. Let A be subset of X closed and disjoint. Now we're getting this train rolling. For any B in B, separate A from B, which we know we can do because B is not an A by virtue of B being disjoint to A, and A is closed and B is a point, and we know compact Hausdorff spaces are regular. So now we can separate them via open sets UB and VB. Choose a, so VB covers B, obviously, and B is closed, a closed subset of a compact space, so it is again compact, so VB as a cover of B has a finite subcover VB1 to VBN. Then set U defined to be the intersection of over all I of UBI. So essentially we're not choosing a finite subcover, and let BI I in 1 till n, let BI be the corresponding indices. And V defined to be the union of all the VB1 BI for I in this index set. Yeah. And the same spiel should work here as well. And I fucked up the I point for the third time. So what do we want? U and V is a disjoint by the same argument. From regularity. Okay, so we know U contains A, U is open, V contains B, V is open, and hence we're done. Oh, this is so great. Okay, compact Hausdorff spaces are normal. So, this was the part we perhaps should have known. No idea. How the hell should we have proven that in our differential geometry course? Like, we haven't been talking about what normal space is, what even paracompact means. I think we just proved it directly, and I'm just using that to now try to prove that it's compact. I'm really interested in how the direct proof worked when looking into the old script. So this is me. Yeah. What would be really cool were if, ignore the compact thing, if we could guarantee that the refinement we get would always consist of small sets, in the sense that the closure of every open set is, let's say, compact. Do we need that? Not sure. All A, B disjoint close admit a separating function. We're not going to prove Urysohn's lemma. I think I would perhaps be able to do that with enough time, but I mean, I've been sitting here for ages already. So let me just, let's just look up Urysohn's lemma. Formal statement. Separated by a function. Okay, we only get that f of a is 0 for all a and a, and f of b equals 1 for all b and b. This does not necessarily mean that the only points where a is 0, the only points being mapped to 0, are necessarily in a. Yeah. So this is what's standing here. They need not be precisely separated. Oh god, these are... Okay, do we need perfectly normal spaces? No, compact Hausdorff spaces are just normal. Oh no, this is going to... this is still going to be messy. Okay, but we're one important step ahead. Of course, continuous f from x to 0, 1, such that f restricted to a is the constant 1 function and f restricted to b is the constant 0 function. Okay. So I'm thinking 3 steps ahead. This I'm not thinking things through. This isn't good. Let's x compact and u1 and u2 a cover, by which we of course mean an open cover. Then let lambda 1 be a separating, be defined this is not a lemma yet, this is an idea. Between u1 without the closure of that and u2 without u1. How do we know these are how do we know these are disjoint? Now the closure of u1 without u2 should be no, it's not the closure of the intersection, or is it? Yeah, no. Oh, we know the, oh god, the closure of the intersection is always a subset of the closure of the intersection of the closures, which is u1 closure intersected with u2 with the closure with the complement so because you know the complement u2 is open, so the complement of u2 is closed, hence this is u1 without u2. Okay, yeah, we at least know that. Similarly, wait, but the this here would be now we're down to calculating stuff, right? This shouldn't be so hard. In our example, we have like this is that without that. Because you know this is u1 and this is u2. No, this is u1 and this is u2. So the closure of u, yeah, let's make this a bit more cleaned up. We have this u1 and u2, and so the closure of u1 is blue, and the closure of u1 without u2 is this, and this should be this half ray, you know. So we should just be left with So my idea would be that the closure of U1 without U2 should just nothing be but okay, so yeah, it contains some. Oh boy, no, I'm incredibly stupid. This like wait, so it's this is that, you know, this is U1 closure, and that's the complement of, yeah, okay, so I'm thinking that this should nothing be but U1 without U2, right? Anyway, similarly we have the closure of without U1 is a subset of U2 without U1 but the closure of U2. Oh, do we know these are disjoint? So if we knew that these were disjoint, these bodies, then we could already show that these two had to be disjoint because they're smaller. Yeah, okay, so U1 closure without U2 cap U2 closure without U1 is nothing but U1 closure cap U2 complement cap U2 closure cap U1 complement equals U1 closure cap. Ew. Yeah, okay, I see. Close U1 complement, which is the closure of U1. U1 is open, so the complement is closed, right? But the intersection of a set's closure with the closure of its complement is nothing but the boundary. So with U2 we have the same U2 cap U2 complement closure. So this equals the boundary of U1 cap the boundary of U2. Oh dear Lord, how do we know that the boundary of these fellows is not intersecting? Because we certainly don't know that for an arbitrary cover, right? Oh God. Oh dear Lord. Because when we have an arbitrary cover, this certainly doesn't have to. When we pick two sets of an arbitrary cover, this doesn't work. Because, let's say we have this open set, and, well, let's just say we have in R2, we have this open set U1, we have this open set U2, which only goes to here, and we have this open set U3, which only goes to here. Then we would have, no matter what. Oh wait, would that be a cover? I thought that no matter what we selected, we would have a common boundary, a boundary with non-empty intersection for all of these fellows. Okay, let's lay U2 and U3 differently. If we had... Oh, right, we can't do that because... so this here is kind of a gap, and this here would also be kind of a gap. So, okay, because... like U1, U2, and U3 would have to be open. So the question I'm trying to answer is, given any cover, can we always pick two elements of that cover whose boundary does not intersect? I have no idea how to prove this. I'm realizing that this is already like the second part of it after the break is 1 hour and 24 minutes long. So, and I think I want to review this at some point, and I want to add chapter marks. So, yeah, I'm not quite sure about that. So we are essentially not very far ahead. So my point would be, if this would work, if we had non-empty boundary, then what we could do was, we should probably just ignore that. Like, assuming we would find some good collection of separating functions, can we do something with that? How could we potentially generalize this to paracompact spaces if we look at compact spaces? Does every open cover have a compact refinement? Stuff like that. Anyway, do we need that the space is locally compact? Because if we didn't know that, then this would be that would be terrible. That would mean that we couldn't say, well, if we have a good enough, a cover that's behaved well enough, that consists of rather small sets, then we can assume that around some part of it is compact, so our logic applies. But if we don't have that, this is kind of absolutely useless. Okay, assuming we could always choose it to be that way with two sets. Wait, if we have two sets, let's just stick to two sets, and let's just prove it anyway. Because with assuming the boundary would intersect, and there. Do I know, in general, paracompact Hausdorff spaces, that an open set is disjoint from its boundary? let x in delta u, then for all v containing x open, some elements y in u and some don't. Oh yes, I always have that. So we don't even need that. Because if x were in u, it's an interior point, so for some w containing x that is in u open. No, so for what I wanted to say, for some w around x which is open, we have w subset of x, so all elements lie in u, hence yeah, hence none in delta u. Okay, yeah. Okay, yeah, we could also prove this using the Kuratowski axioms and the definition of the interior as the complement of the closure of the complement, and the boundary is the intersection of these two. Yeah, whatever. So this always works. Yeah. Let's go to white again. If u1 and u2 is a cover, then boundary u1 and boundary u2 is empty. Prove. Let x in the boundary of u1, in particular, we know that x is not in the boundary in u1 itself because u1 is open. Since u1 and u2 is a cover, u2 must be the cover element containing x, because there is no element remaining. In particular, x is not in u2, in the boundary of u2. Wow, this looks ugly. So if x is in u1, x cannot be in the boundary of u2. We have shown that there cannot possibly any point in the intersection, so no point satisfying both things. Okay. So let lambda1 be lambda1 restricted to u. Yeah, let's just assume that so this is not empty. Okay, yeah, precise. So these are disjoint. Da 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 da. Is this separating function already what we want? So we do have, all we have guaranteed is that we do have, give me a second. Let's begin a new page. Let X compact and Hausdorff and U1 and U2 a cover. Come on. Then the closure of U1 without U2 disjoint from the closure of U2 without U1. Let lambda1 be a function which is, so let's call this A and this B. I mean, the intersection is an open. Shouldn't there be a simpler argument for that? Because there should be an Shouldn't the space split up into the intersection of U1 and U2, which is open, and the complement, which has to be the closure of the symmetric difference, and so let lambda1 be the separating function, so lambda1 in A is constantly 1, lambda1 in B is constantly 0. All we know is that we have A, we have B, but it might be it's 0, it's 1 over here and 0 over there. Might be that it's here 1 or here is 0 occasionally, because like, yeah, we don't really know that though, right? Perhaps we would have to look into the proof and see whether under some additional guarantees, like for such a nice cover or something connected sets something, that we would actually be guaranteed the existence of a precisely separating function, but this cannot happen. And yeah, so we have that. Precisely separating? No, certainly not. because a precisely separating function is what we're looking for. I mean, it's not allowed to be one anywhere else, right? Because, yeah, the support should lie in the support of the function should be inside of U1, but if it can be 1 at some point which is completely outside of anything, we don't know where this 1 should be, then this is a bad thing. Or should we just separate our function from... we could perhaps just separate our function from... crap. No, this is not any help. Oh wait, this isn't bad. We don't need precisely separating. Okay, so Q first is the support of lambda 1 subset of U1. Second is the support of 1 minus lambda 1 inside of U2. So, U2 without U1 is essentially X without U1. I'm realizing just now. Because, you know, the U2 without U1 is the same as U2 with U1 without U1, because the without U1 is just cancelling the union we just added, and U2 cap U1 is just X, so this is the closure of X without U1, but which is the complement of U1, which is closed, so this is nothing but X without U1. Okay, so this is nothing but X without U2. Okay, now this is interesting. So we are these disjoint? Yeah, I think, okay, these being disjoint is precisely should be precisely the definition of a cover, because, you know, U2 complement intersected with U1 complement is the same as U1 cap U2 complement is X complement is the empty set. Oh wow! I wouldn't have to do all this weird boundary stuff. Oh wow. Similarly, U1 cap something cap UN all to the complement is also union something union UN complement is also equal to 0 for any cover. Oh god, yeah. And oh god, and this is only the compact case with a two-element covering. This is going to be so much worse. But I'm probably calling it a failure. I'm not going to finish. But at least that's a solid partial result if we can get that right. So yeah. Now, the support of lambda 1 is the closure of all the x's where lambda 1 is not 0. Set of elements where lambda 1 is not 0 is contained in the complement of B. So this is, which is, yeah, the closure of the presupport, we called it. Now, the things which are not 0 cannot lie in B, because by definition of the separating function it is 0 over B. So this is in the complement of B. Yeah, what I call B is that, and B is right, and B is that, which is that, which is that, which is just the complement of so this is just U1. So the presupport is contained in U1, so the support, which is the closure, is contained in the closure of U1. Crap! This is not enough. We need more than that. We need that. We need that the support of lambda 1 is in U1 and not in... Wait, have I just completely confused U1 and U2? Because this doesn't make any sense that it's in the... So the B to the... What? I'm having a complement issue here. Oh my god. Oh wait. Okay, no. This makes sense. It's just a bit too weak. God damn it. I think I'm almost there for this thing. I'm just missing something. And yeah, as mentioned, this is just a special case, but I'm gonna call it a day. I hope this was as boring as it was doomed to be, because that's just the reality of how these things work, at least for me, and at least for me very, very frequently. It was kind of an extreme setup because I just didn't look up any proof whatsoever, and I'm perhaps, when I have time, going to revisit that, and I'm going to add chapter marks. If you have any topics I would like to hear me talk about in a more organized fashion and prepared and going through the proof, then tell me. But else, yeah, I hope this was interesting to whoever watched that. And yeah, I guess that's it. How do you end this kind of